viewers, welcome to this series of lectures on solid state. The contents of these lectures pertain to Unit 4 of the third paper of BSc first year students. You must be wondering that you have been learning about solid state right from your early school days. So what are we going to do here? So what I am going to do here is I will try to recapitulate what we learned about solid state earlier, and then try to build on that to give you a comprehensive view of solid state as we know of, as it is required at this level of understanding. So what we will do is, the today's session has been planned as follows. I will start with talking about solids as a state of matter. Thereafter, we will talk about what are the basic characteristics of solids. Again, it's very trivial things, but for sake of it, we will try to build on that. Thereafter, we will see how do we classify solids in terms of the constituent species and the nature of interactions and things like that. Thereafter, we will briefly touch upon the difference between amorphous and crystalline solids. And towards the end, we will talk about the basic laws of crystallography, and thereafter we will quickly sum up what we have done in today's session. So let's make a beginning. Let's make a beginning by starting by trying to define what is chemistry. I'm sure that you must have come across something similar kind of a definition of chemistry, whereby we can say that chemistry can be defined as a study of matter in terms of its structure, composition and the change or the properties of matter. And what we are going to do in this series of lectures is we are going to talk about one aspect, that is the structure of one of the states of matter. So that is what is our, I am trying to put things in perspective. So it means essentially in this series of lectures I am going to touch upon the structural aspect of matter. Okay. So because that is one domain where chemistry focuses on. Okay. Having said that, let's quickly recall what we know of from our earlier days, that matter exists in different states, different physical states are there, and then we know that solids, liquids, gases, they are the commonly observed physical states of matter. In addition to that, we have a state of matter called as plasma, neutron star, white dwarfs, black holes, and nowadays we talk about Bose-Einstein condensates. There are a wide range of physical states of matter we talk about, but by and large we will try to focus attention only on to three states of matter which you are familiar with, that is the solids, liquids and gas. Let's take an example, say of water. Water we know exists in three different forms: as liquid, what you use as water, and then we got ice as a solid state of water, and water vapors. All of these are important for the sustenance of life. Now we also know that the physical states of substance can be changed by suitable change in energy. As we just know, okay, so suppose you got ice as a solid, you warm it up, it becomes liquid, you heat it further, it becomes vapor or the gaseous phase. So that means basically by giving more and more energy, we can change the physical state of a given substance. For example, we can go from gas to solid to liquid to gas or vice versa. So all these processes are well known to us. Now let's take what happens in the course of, say, if you are trying to heat a solid. Let's see what is happening at the molecular level. Suppose I have got a solid here. If I heat it, we know that as the temperature comes to the melting temperature, the solid melts, and then what you get is a liquid here, and then thereafter if you heat it further, the liquid gets warmer and warmer, and at the boiling point it boils off, it vaporizes. Okay. So what you have is it gets converted into gaseous phase. Thereafter further heating, it will make it to hot gas, and if you do the reverse process, you can start with hot gas, cool it up, it will become cooler gas, cool it further, it will become liquid, further cool it down, it will become colder liquid, if you cool it further, it will become solid. Okay. So these processes are there in terms of the change in energy of the substance. So there are two ways of looking at matter. One is a microscopic view, one is a macroscopic view. Let's try to see what is the difference between the two kind of views. In terms of microscopic view, when we try to look at matter, basically matter can be seen as a collection of atoms and molecules. On the other hand, if I try to see in a macroscopic world, how do we look at matter? Matter can be seen in terms of the associated bulk properties, that is, what is the mass of the matter, density, entropy, energy, color, etc., etc. So, when you talk about macroscopic world, we talk about things as a macroscopic way, as a totality of things, whereas in microscopics we talk about the atoms and molecules. So, and the crucial thing here is the macroscopic properties of matter are governed by what is there at the microscopic domain, because that is very, very crucial. We'll build on this as we proceed further. Now, this picture just gives you an idea about if I go from solid to liquid to gas. So, we see that as we go from say solid state to liquid to gaseous state, the compressibility or the entropy is increasing. On the other hand, the density and compaction is decreasing in this direction. Okay. So, that means different states are characterized by different kinds of macroscopic properties with them. Let us look at what are the characteristics of solids. As I mentioned earlier also, all these things are known to you. I am just trying to quickly recall for you what we learned earlier about solids. We know that solids are characterized by, everybody knows that they have got definite shape, mass and volume. Further, all solids are having very high rigidity and low compressibility. Further, they are very hard, we all know that. They lack fluidity. It is in contrast to what happens in case of liquids and gases. They are fluid like, they flow, whereas solids do not flow. Then low diffusibility, because we know that gases diffuse readily, even liquids can show diffusion property, but in case of solids the diffusibility is very, very low. Okay. So, there are typical characteristics of solids as we know of in terms of the microscopic world. Now, going further, we also know that crystalline solids exist in different shapes. This picture gives you 7 different kinds of shapes, because typically this is crucial here, because what happens is you take any crystalline solid from any source whatsoever, you will find that it belongs to one of these 7 crystal systems, because this 7 is a very crucial number for us, because there is no crystal system which goes out of these 7. And I am going to show you some crystals here. We can see that they come in different kind of shapes. We will talk more about it as we proceed. Now, another thing which we all know of, that solids are hard, and typically what we see here is, this is very important here, that different solids are hard to different extents, and typically what happens is any solid which is harder than the other one will be able to give some kind of a scratch or leave a mark on that. And based on this property, it is typically used by mineralogists. In case of minerals, there is a scale called as Mohs scale of hardness. What is done is, this is a scale which ranges from 1 to 10. At 1 we got talc, at 10 we got diamond. Diamond is the hardest matter we know of, natural material, and talc is the softest one. That means any material, suppose I take gypsum or calcite. Calcite if I take and try to use calcite to mark on gypsum, it will leave a scratch on gypsum, but reverse will not be there, because calcite is harder than gypsum, so it will leave a mark on the softer material there. So, that is the kind of scale we have. Going further, we know that crystals have got distinct faces. This is very, very important. You must have come across some crystalline materials. I can show you some of them. These are sugar crystals. Now, in sugar crystals, typically what you see is that there are distinct faces. Faces means there will be smooth surfaces of the kind as shown over here in these pictures. This is sodium chloride crystal there. This is quartz. Quartz is a very, very well known crystalline solid. Yet another one is that crystals show cleavage property. What it means is, since crystals have got nice faces, we talk more about it as when we talk about a structure, internal structure of solids. So, what happens is, if we take a crystalline material and just try to break it or try to chop it off or try to slice it, we can make it cleave. And what happens is that if I take a crystalline material and cleave it, so this will give me similar materials. That means there will be smaller versions of same material. That is, if I take a crystal of say alum, then if I can cleave it, I will be getting smaller versions of alum, but that will be similar to what we had as the larger material. Okay. So, that is the meaning of cleavage here. This is a nice picture showing you the cleavage in case of mica. In case of mica, we got thin sheets thin layers are there, each layer can be separated out very comfortably with even fingers also we can do that. Now, besides these characteristics, we can even try to have a look at how do we classify solids, because we said we will talk about typical characteristics. Having done that, now we try to see how do we classify solids. And one of the typical bases used for classifying solids is what is the nature of the species which are constituting a solid, and also what is the kind of interaction between them. On this basis, we can classify solids as follows. One of the very most commonly kind of class is ionic solids. Yet another one is molecular solids. Then we got network solids, and then we got metallic solids. There are four. This is one way of doing it. There are many more different ways of looking at the classification. So this is the most commonly used classification. In case of ionic solids, what do we have is, as the name suggests, ionic solids will consist of oppositely charged ions which are held together by Coulombic interactions. Typical example I can take, say, of sodium chloride. What happens in case of sodium chloride? The sodium ions and chloride ions, they are held together by ionic bond. So this is a typical simple picture of sodium chloride here. Now, in case of molecular solids, as the name suggests, the species involved are molecules, and these molecules are held together by weak interactions like van der Waal interactions, or maybe dipole-dipole interaction, or hydrogen bonding. So there are a variety of examples we can take. Let me take two examples for you. The first one, say, dry ice or solid carbon dioxide. This consists of the molecules of carbon dioxide which are held together by weak van der Waal interactions. So any solid which is held by weak van der Waal interactions will be easy to handle. It will have low melting point and things like that. Another example is, say, ice. Ice is an example of molecular solid. In this case, the water molecules, they form crystalline solid, and they are held together by hydrogen bonding. So what you see here is that this red is oxygen atom, then these two are hydrogen atoms there, and these water molecules are held together by hydrogen bonding. They form nice crystalline materials. That is how ice looks like. Yet another class is your metallic solids. In case of metallic solids, we know that metals can be visualized as typically what's called as the electron C model, wherein what we see is that the positive kernels or the metal cations are orderly arranged into a sea of electrons. So it's called as the electron C model. Typical examples I can take iron, copper, any metal for that matter. So what happens is, so these metal cations are held together in ordered arrangement, and the electrons are mobile there. That leads to the conductivity and conductance and things like that. Yet another class is your network solids. As the name suggests, network solids, they form networks, large networks of covalent bond interaction, very strong interactions there. So typically there will be atoms which are held together by strong covalent interactions, and best example I can quote it of, say, diamond. That's the best, the hardest material we know of, natural material. So in this case of diamond, the carbon atoms are held together by covalent bonds. Each carbon atom is attached to 4 more carbon atoms through covalent bonds. Since the covalent bonds are the strongest ones, so this will be very, very hard. Okay. Graphite is another example of a covalent solid, network solid. In this case, what you see is that there are layers. There is a two-dimensional layer. Each layer will be called as graphene, wherein the carbon atoms are linked together by covalent bonds, and between the two layers there are weak van der Waal interactions. That's why graphite is softer, because of this third dimension there. In two dimension, in the layer part, it is covalent linkage, very strong, but between the two layers the interaction is weak. That's why it is very soft. I wanted to talk about two more terms which are very, very important when you talk about solids. That solids can be classified into two broad groups. One are called as amorphous, one is called as crystalline solids. This is important to understand. Amorphous means amorphous, means without face, without structure. That means they don't have a form. That means without form. That means it's not a crystalline material, it is very random kind of a thing. On the other hand, crystalline solids are well defined solids there. And in terms of the molecular structure, what you find is that the arrangement of the species which are constituting the solid is very, very well ordered one in case of crystalline solids, and it is not so well ordered in case of amorphous materials. So, glass is an example of amorphous material, whereas quartz is a crystalline material. So, what I am showing you here is there are two pictures. One is the sulfur, this is amorphous sulfur, this is crystalline sulfur, both are available in nature. So, it actually depends on how long has it taken for this material to come into being, what are the conditions under which this has been formed. This is another example of, as I just mentioned, quartz and glass. You see that it's a two-dimensional structure here. So, quartz is a silicon dioxide which is highly crystalline material here, whereas glass is amorphous, that means it has order but of a lesser order. This is a similar picture of silicon dioxide again. This is a crystalline material, ordered material. Amorphous, it does not have that kind of a long range order, it has order which is very short ranged. So, that is the way we can look into the amorphous and the crystalline materials. Let us see something which is very useful for us to understand, very important for us to know, that crystalline solids are anisotropic. Anisotropic means having different properties along different directions. That means, if I take a solid and measure its property in a given dimension, I will have one value, another dimension it will have different value, and so on and so forth. That means, it has got different values in different directions. This seems to be some kind of a paradoxical, because we just said that crystalline solids have got long range order. If they are ordered, then why should have different properties in different directions? The reason for that is, if we look closely to this, we find that the arrangement of the species which are constituting the solid, that is not same in different directions. Let us see it here. So, start from here, as I move around here, we find that there is a sodium ion there is a chloride ion, sodium, and so on and so forth. That is how it goes. Whereas, in this direction it is slightly different here, in this direction it is a different way. Okay. So, when I move in different directions, that is, you come across different set of ions. So, since the arrangement is different in different directions, the properties are different, thereby the crystalline solids are anisotropic. On the other hand, if I look at amorphous material, they have got short range order, but on long range their order is not there. So, in such cases, irrespective of which direction I will look into, say I start from this direction, go like this or like this or like this, if I go in any direction, on an average what will happen is I will come across similar kind of arrangement, because it can't be same, because it is no ordered arrangement. So, there will be some ordered region, there will be some disorder, some order, disorder. If I go in different direction, maybe there is a disorder, then order, and so on and so forth. But on an average, what will happen is that we come across similar kind of a arrangement. So, thereby amorphous materials are isotropic in nature. This is a typical thing which actually boggles you down sometimes. Why is it so? So, reason for that is the arrangement on an average happens to be uniform in different directions. Before we proceed, let us see what we have done so far. What we have done is we try to see solids as a state of matter, and then thereafter we have seen what are the characteristics of solids and some general properties about solids, how do they look like and things like that. And now we just talked about the difference between amorphous and crystalline solids. Now, let us try to take up some basic fundamental laws of crystals or crystallography, because they are very important, because eventually towards the end of this series of lectures we will talk about how do we use X-ray diffraction to find out the structure of a solid. So, that is what is our ultimate objective. So, to begin with, at the trivial level or the basic level, let us understand what are the fundamental laws of crystallography. The first law is called as the Steno's law of constancy of interfacial angles. What it states is, it states that the angles between two corresponding faces on the crystal of any solid chemical or mineral species are constant, and they are characteristics of the species, to the extent that if I come across some kind of a solid material and make a measurement of the interfacial angles, so by knowing those interfacial angles, I can even identify what mineral I am talking about. So, they are very important. It was done somewhere in the third quarter of 17th century by Steno. Let us understand what is the meaning of interfacial angle. As I just mentioned, that any crystalline solid will have number of faces and they will meet at some kind of a boundary here. So, there is an angle between these two faces, that is called as interfacial angle. there is a specific way of defining this interfacial angle. To define this, let's see this picture here. This gives you a schematic representation of a crystalline solid. So what you see is this is one face, another, these things are different faces of the crystal here. And what I am showing you here is that to measure the angle between say this face and this face, what is done is we draw a perpendicular on this face and also on this face. Wherever these two perpendiculars meet, this is the angle what is called as an interfacial angle. Okay. So, then another alternatively we can define it to be somewhere here. So, this angle and this angle are going to be the same. That means the interfacial angles are measured between the lines drawn perpendicular to the faces in question. Now, suppose I want to find out interfacial angle between this face and the next one. So, in this case this perpendicular will stay as such. I draw a perpendicular on this face now, and wherever these two meet, this angle here which I will get will be my interfacial angle there. So, all these different faces will have different values of interfacial angle. That is one crucial aspect of defining what is interfacial angle. The interfacial angles are measured with the help of a device called as goniometer. This picture gives you a very schematic or sketch of how to use a goniometer. Now, one thing which is very important about interfacial angles is that this is the crux of our Steno's law, that is, for any two crystals of a given substance, irrespective of its size, locality of occurrence, or whether they are from natural or man-made material, no matter what is the source of a given crystal, that will have same set of interfacial angles. That is very, very crucial. If you remember that I just mentioned about it a few moments back, that is, if I take any mineral and measure interfacial angles, that measurement can be made use of in terms of characterizing that particular mineral there. Okay. So, that is the basis of that kind of characterization lies in the Steno's law, which says that if I take any say if I take sodium chloride, whether I take from say natural material or I crystallize it in a lab or take it from some other source, I take it from US or take it from China, you take it from India, irrespective of where do I take it from, it will have same set of interfacial angles. Okay. Now, second important law of crystallography is Hoy's law of rational intercepts. What basically happened was that Rene Hoy was actually working with the crystals of calcite, and he observed that when he accidentally dropped that crystal, he observed that the crystal cleaved into straight planes, and then irrespective of the size and shape of that, the crystals, all the fragments of the crystal were rhombohedral in shape. That is very characteristic of the particular material, that is calcite. And then these observations are now known as Hoy's law of rational intercepts. What it reads is, that is, if I take any crystalline material and if I look at the faces of that crystal, if I suppose any crystal, I choose my say 3 axes because it's a 3-dimensional material, and then look at the different planes or different faces of the crystal, then the ratio of the intercepts on these 3 axes for different faces can always be represented by rational numbers. We will elaborate on this when we move further to about maybe at a later part of this, when you talk about Miller indices and things like that. But for right now, we will suffice by saying that the different faces of the crystal, when they cut the crystallographic axis, the ratios can be given in terms of rational numbers. But going further, Hoy made a very, very crucial observation, or rather prediction. He concluded that the outward symmetry of a crystal, it implies that it has to have some kind of a regular internal structure. In principle, what he meant was that he proposed the existence of a small crystal unit. That means, if I take a large crystal is to be formed, on the at the basis of that there will be some small ordered arrangement that will actually grow up to give you a large crystal, and that small thing nowadays we call it as unit cell. In addition to these two laws, there is one more law, what is called as law of constancy of crystal symmetry. It states that all the crystals of a given substance have same elements of symmetry. This aspect we will take up later when we talk about molecular symmetry and crystal symmetry. At that stage, we will try to touch upon this, because it's difficult to appreciate this at this stage without knowing anything about the symmetry. Let's quickly sum up what we've done today. What we've done today is we are talking about solid state, and we're talking about solid state as one of physical states of matter. In this context, we started with talking about different physical states and their interconvertibility in terms of energetics. That means if we give energy to the system, how does the physical state change, or take energy from it, how does the system change. Thereafter, we touched upon different characteristics of crystalline solids, that is in terms of their hardness and then cleavability and many more things. Thereafter, we talked about the classification of solids, and in this context we tried to use the basis as the nature of species constituting solid and also the interaction between them, and on that basis we kind of classified solids into ionic solids, molecular solids, network solids and metallic solids. Thereafter, we did also talk about the amorphous and crystalline solids, and we tried to differentiate between the two because that's very crucial, and we realized that amorphous solids are isotropic in nature, whereas crystalline solids are anisotropic in nature. And towards the end, we talked about different laws of crystallography, and we talked primarily two laws. One is the Steno's law of constant interfacial angles, and second is Hoyle's law of rational intercepts. And the third law we did touch upon, we did make a mention of, that is law of crystalline symmetry, and we didn't elaborate on that. We'll talk about it as we move further later on. And having done all this, in the next episode we will try to build on what was that Hoyle's statement, that is for a given crystalline material to have a given shape, it must have some kind of an internal order there. So we will try to learn about what is the internal structure of solids, how do we talk about internal structure, how do we represent that. That is what we are going to touch upon in the